Okay, so let's get started. Let me start with a few announcements. The assignment 2 is due on Friday. Next Wednesday, we'll have an in-class midterm. If you've been following the lectures from home, that's fine. But next Wednesday, we want to do, the midterm will be in class and proctored. Next Monday, we'll do a review for the midterm. For the midterm itself, it's going to be closed book. You can bring one double-sided page of handwritten notes. And the exam itself will provide a formula sheet. With some useful formulas. Okay. Any questions about the midterm next week? Yeah, the paper size. Yeah, so you can't bring in a giant poster of notes, just a normal letter size paper. Does that answer your question? Okay. Any other questions? Okay. Let's call this announcements. Let me start with a very brief summary of what we did last time and so far. So we found that the Lagrangian can be written as T minus V. We saw that Hamilton's principle was effectively gave the same result as D'Alembert's principle, and Hamilton's principle was that S, which is defined as the integral from some time to some other time of L of Q, let's say Qi dot, and T, is stationary. That gives us the equations of motion for a system, which are the Euler-Lagrange equations, which you all know by heart now, which is d by dt of diL by diqi dot minus diL by diqi equal to 0. And we also saw that given constraints, Fk of the Qi's then we had generalized forces Qij, which are given by lambda I, some Lagrangian multiplier, d by dt of di fi by diqj dot minus di fi by diqj. And so we saw an example with a hoop rolling down a plane where the constraints were related to forces that go with those constraints. For example, we saw that the rolling without slipping constraint was related to the torque that makes the object turn. Any questions about that? So now we'll examine some of the properties of this function L. So the first property is that L is invariant with respect to what we call point transformations. These are point transformations of the generalized coordinates. So what does this mean? So in general, one can define a transformation of coordinates from one set of generalized coordinates to another set of generalized coordinates, so let's say from Q to Q prime. The most general type of such a transformation is called a contact transformation. That's when the Qi primed is a function of the Qi, the generalized velocities, and time. That is the most general type of what we call a contact transformation. Okay, and for this transformation to be allowable, there are certain conditions that this function Qi prime, the Q, must satisfy, such as being continuous, differentiable, invertible, which means that the Jacobian of the transformation is non-zero. Now, a point transformation is a special case when the Qi primed only depends on the Qi and potentially time, but not the velocities. So an example of a point transformation is the transformation from Cartesian to polar coordinates. So in Cartesian to polar coordinates, the radius r should be a function of the generalized coordinates x and y. In Cartesian coordinates, that function is actually given by the square root of x squared plus y squared, right? And similarly, theta, which is a function of x and y, is the inverse tan of y over x. So that is an example of a point transformation. And it's actually almost okay, right? But if x equals 0, there's a problem. And that's the case when r equals 0. So it's not completely continuous right at the origin. So you have to write it as a special case when r equals 0. And so some of the properties of point transformations if lines don't intersect in the Q space, they don't intersect in the Q prime space. So it preserves the properties of lines. That if they don't intersect in one space, they won't intersect in the other space. And that's very simple to understand. Is, for example, you have a line in Cartesian space, two lines in Cartesian space. So all the points on either belong to one line or on the other line. If those lines were to intersect in, say, polar coordinates, that means that there's one particular point that maps where two different points on the XY coordinate system map to the same point on the polar system. And so what it's really saying is that each point maps to a unique point in the other space. Okay? And then the other thing is infinitesimals are preserved. So there's an example in the notes where you have a rectangle, or I guess it's a square, in Cartesian coordinates. If you map that into polar coordinates, and you draw the polar coordinates as two axes, then you'll get some sort of shape that looks like this. So I've mapped these 4 individual points. And when I say infinitesimals are preserved, I mean that if in the XY system I had made the square infinitely small, then it would actually map to a square in the theta r plane. So Lagrange's equations the equations of motions describe the evolution of a system through configuration space. All right, so for example, that's the path of a cannonball. What Lagrange's equations do is describe the shape of that path. Now, you can consider adding time as an additional coordinate in your coordinate system. Well, maybe I'll put T on the bottom since we're more used to it. So now, just for the simplicity of writing on paper, I only have one space coordinate. Now, a system, the Lagrange's equations of motion describe the path that a system takes through space and time. So in the top plot where I have the cannonball, the path of the system is still dictated by the initial conditions. And there are multiple possible paths for the system that it can take in the coordinate system. But as soon as you add t, then there's only one path it can take. Now, the Lagrangian is invariant to point transformations. So let's write that down and we'll think what it means. So remember, L is the kinetic energy minus the potential energy. So it's a number, right? You can take the system at any point in time, and you can calculate its kinetic energy. That's a number in joules. You can calculate its potential energy, and you can calculate this quantity that's called L. And we know that when we write L as a function, applying the Euler-Lagrange equations to L gives us the path of the system through time and space, right? But L is just a number that you can calculate and actually put in a value in joules. It's we call it excess kinetic energy, right? So it's actually not that surprising when we say that L is invariant to point transformations. A point transformation is just a change of coordinates, right? So if you have a system, whether you decide to calculate the velocities in Cartesian coordinate or you decide to calculate the velocities in polar coordinates, ultimately when you calculate the kinetic energy, you're going to get the same number if you're in a, say, inertial frames of reference. And the same goes with the potential energy. So you might have a different value of the potential energy. Let's say you're calculating gravitational potential energy and your transformed coordinate system is at a different height, then the actual value of the potential energy will be different because you're at a different height. But we already know that adding a constant to the potential energy doesn't make any difference. So the equations of motion, which are given by the Euler-Lagrange equations, are invariant to that specific choice. And so all it's saying is that the system can be described by any set of coordinate systems, and its evolution is unchanged. And that's a good thing, right? You wouldn't want the evolution of the system to change based on your choice of coordinate system. So it's actually a very simple statement, but it has profound consequences that we'll see later when we consider symmetries and how they result in conservation laws. So what that means is that the Euler-Lagrange equations are invariant and do not depend on a specific choice of coordinate system. So it says we can choose to describe system in polar coordinates, or we can choose to describe the system in Cartesian coordinates. It's not going to affect how the system evolves. And this is sort of almost true. When I said that we can add the time in as one of our coordinates, and any inertial reference frame will have the same description of the system. If that other inertial frame is moving really, really fast, then that's not true anymore, right? Because time doesn't go the same way in two inertial frames of reference that are moving very fast with respect to each other. That's special relativity. So in principle, you can't just add time in as an n+1 generalized coordinate and treat it separately. And you know from special relativity that if you want the system to be described the same way, then time has to be treated on the same footing as the other coordinates. And so if the one coordinate transforms into another coordinate, a space coordinate, then the time must also transform. Those are called Lorentz transformations. And if you remember from special relativity, when you go from one coordinate system to the other, time is not treated independently. So you must treat time as a coordinate. that can transform as well. For example, the Lorentz transformation. In special relativity. So let's do an example. Of describing a system in two different coordinate systems. So let's describe a particle in a gravitational field. So Lagrangian of a particle in a gravitational field is T, kinetic energy, which is given by a half mx dot squared plus y dot squared plus z dot squared minus the potential energy, which we'll set as mg times z. So we'll have gravity in the negative z direction. So the Euler-Lagrange equations, so that's d by dt of di-L by di-x dot minus di-L by di-x, right? And so that's easily going to give us that mx double dot equals 0, or since equal to 0. These are easy to do in your head, right? So the Euler-Lagrange equation give us the result that you would expect. Now in polar coordinates, the same system would be described by the kinetic energy, which is a half m r dot squared plus r squared theta dot squared plus z dot squared minus mg. All right, that's the kinetic energy in polar coordinates, which I think that's question 1 of assignment 2. And so here again now, if you use the Euler-Lagrange equations, you'll get the equations of motion that r double dot is equal to r theta dot squared. Theta double dot is 0, and z double dot is minus g. I believe that's correct. So I know that. And so that's also a straight line. Okay, so the choice of coordinates doesn't change how the system evolves. And that's a good thing, right? All right, so the next property, 2, is the addition of Lagrangians. So if you have two systems, described by a Lagrangian for the first system and a Lagrangian LB for the second system, then the total system is described by L equals LA plus LB. So if you have isolated systems, each with their own Lagrangian, you can describe the sum of the isolated system by the sum of the Lagrangians. So if that's the case, right, I mean, this should be trivial, but the first system is described by d by dt of di LA by di QI dot minus di LA by di QI equals 0. The second system is described by the same equation, but with b's in it, di LB by di QI dot minus di LB by di QI equals 0. And simply by the properties of adding the derivatives, it should be clear that d by dt of di by di QI dot of LA plus LB minus di by di QI of LA plus LB is equal to 0. The next property is multiplication of L by a constant call that constant K. And so the same system is described by L and by K times L. Alright, so let me just write the Euler-Lagrangian for the equation for the system that's described by K times L. So I have d by dt of di by di QI dot of K times L minus di by di QI of K times L equal to 0. And you agree that the K factors out. And since it's equal to 0, the K can just be removed. So if you multiply the whole Lagrangian by a constant, then that does not affect the equations of motion. And we did a specific example last time where we found that, at least for a free particle, that constant is related to what we define as mass. And it's only the ratio of the terms in L that matter, not the overall scale of the Lagrangian. And so multiplying the whole Lagrangian by some number, in some sense, is equivalent to changing the definition of mass, the units of mass. So multiplication by K is somewhat similar to changing units of mass. Of course, we hope that the evolution of a system doesn't depend on what units we choose to measure mass in. All right. The fourth property is addition of the total time derivative. And a lot of these properties may seem very trivial, but we'll use them later. So that's why we go through them all. All right. So the equations of motion are unchanged if we add the total time derivative let's call that a function f of our variables. In fact, it could depend on the QI dots. To L. So let's say you have a function f, you take the total time derivative of it, and you add that to the Lagrangian, then the postulate is that the equations of motions are unchanged. So maybe that's not super obvious. That comes from Hamilton's principle. So we're going to go from L to L plus df by dt, right? So consider the action S, which is given by the integral of L plus df by dt, dt between some point Ta and some point Tb. All right. Hamilton's principle is that the equations of motion are given by requiring that S is stationary. Okay. So if I calculate S now, So it's the integral of a sum, so it's the sum of integrals, right? So the first integral is what we usually have, and then the second integral from TA to TB of df by dt dt. Alright, and so that is, the action is the integral from TA to TB of L dt, plus, now the second integral is trivial, right, because you're integrating the derivative. And so that's f evaluated at TA minus f evaluated at TB. Now remember, when we take the variation, what we're doing is we have 2 points in space, in this case in time, and when we're doing the variation of S, we're finding the path where S is stationary, right? So when we do the variation of S, we're considering all these different paths, but all those different paths are fixed at TA and TB. So the variation, if you go back and you look at your notes when we did derive the Euler-Lagrange equation, the variation is 0 at the endpoints. So when we do the variation of S, right, we calculate S at the varied values of the Q's and the Q dots, but the variation of those values at the endpoints is 0. That means the term FTA and FTB don't vary, and so they don't contribute to the variation of S. And so then the variation of S is the variation of the integral from TA to TB of L delta T, plus, in principle, the variation of F evaluated at TA and F evaluated at TB. But those two terms are 0. And so the conclusion is, if you add a total time derivative to the Lagrangian, because of that, because of Hamilton's principle, the equations of motion come out the same. Okay? All right. So the next property is the case when the Lagrangian does not depend explicitly on time. depend explicitly means that the partial derivative with respect to t is equal to 0. Obviously, the Lagrangian depends implicitly on time, since presumably the particles are moving around and changing energies, or exchanging at least kinetic energy for potential energy. But for example, the potential energy doesn't depend on time. The gravity of the Earth isn't changing with the function of time, as a function of time. Okay. So we actually already looked at this particular case in one of the examples in the previous chapter on D'Alembert's principle, where we made that assumption as well, and then we found that energy was conserved. But let's treat it from the perspective of the calculus of variations. So recall, we spent some time going through this in Chapter 2, and this was equation 256 in the notes. That if we had some integral from, well, we did it with x's at the time, of a function L that depends on a bunch of function y's, so y1 to yn, y1 primed to yn primed, and x dx, we found that if dial by dx equals to 0, that instead of the Euler-Lagrange equation, we had a more simple equation that the sum from I equals 1 to n of the yi primed multiplied by the diL by di yi primed minus L was equal to a constant. Alright. And remember, y primed is dyi by dx. And so that's something that we demonstrated purely mathematically, right, based on the Euler-Lagrange equations. So obviously this is still true if we call the y's q's and the x t, right? So that means that if diL by dit, I'm just going to write the same equation and change the name of the variables, if diL by dit equals 0, then the sum from I equals 1 to n of the qi dot multiplied by the diL by diqi dot minus L is equal to a constant. Let's call that constant little h. In this case, it has a name. It's called the Jacobi integral. Okay, so that's a result that when we did it in Chapter 2 on the calculus of variations was maybe a little bit obscure why we would even consider it. But the reason is that this equation here only contains first order derivatives in the qi, right? So specifically when L doesn't depend explicitly on time, then the equation of motion can be replaced by this equation where, remember, normally the equation of motion from the Euler-Lagrange equation has second order derivative, right? Because it's that d by dt of the term that depends on the velocity, so you get double dots. Here, the equation only has single dots, so in principle, it's a first order differential equation rather than a second order differential equation. So it is a simplification, right? So we showed that h, or this thing is equal to a constant, right? So specifically, if di L by di T equals 0, then dH by dt equals 0. All right, so we only require that L doesn't explicitly have T's on it, and then H is a constant. And if H is a constant, that means that its derivative with respect to time is 0. That's a concept that's good to remember in general. If something is constant, its total time derivative is 0, which is obvious, but it's something to keep in mind. So let's examine this quantity H a little bit more. Okay? So let's make 2 more assumptions. So that we can understand H a little bit better. We'll assume, number 1, that the kinetic energy T is what we call quadratic in the velocities. So we'll assume that it can be written as the sum over I, oops, too many squiggles, sum over J of A, oops, let's use J's and K's actually. So assume specifically that the kinetic energy has this form. And that's true in most cases, and in fact you did that again in assignment 1, or assignment 2, the first question, where only in the last case that kinetic energy was not true. So for like well-behaved coordinate systems, the kinetic energy only depends on the coordinate velocities squared or multiplications of the coordinate velocities. So in Cartesian, it's obvious, right? In fact, the jk only has terms when j equals k, because the kinetic energy is x dot squared plus y dot squared plus z dot squared. And so there's no terms that have more complicated terms in it. And then 2, we'll assume that the potential energy V does not depend explicitly on velocities. That's just to make the math simpler. In fact, potential energy very rarely depends on velocities. And the only case where we had to do a lot of extra math was in the specific case of the Lorentz force, where the force in the magnetic field actually does depend on velocity. And so what we'll do is actually also still applies in that case, but the math is more annoying and would hide away from the takeaway message here of what this quantity H actually is. All right? So given those 2 assumptions, consider this. The derivative of L with respect to Qi dot, so that's di by di Qi dot of T minus V, right? but we just said that V doesn't depend on Qi dot. And so di L by di Qi dot is equal to di T by di Qi dot, right? So let's calculate di T by di Qi dot given the form that we just imposed on T. So that's di by di Qi dot of the sum of J up to N, the sum of K up to N of A, JK, QJ dot, QK dot. Or I guess did I forget to put a half in front of on the previous page? No. So that's just writing out T as what we imposed the form would be like, right? So if I take the Qi dot partial derivative on the inside, right, it's di by di Qi dot of AJK, QJ dot, QK dot. So at one point in the sum over the J's, the QJ is going to be equal to the Qi. And so the derivative, the partial derivative with respect to Qi dot is going to be the term that goes with that Qi dot, right? So that's a half times the sum over J of Aij Qj dot plus the sum over K of exactly the same thing, Aik Qk dot. Right. If you look at the term with the double sum in it, right? I take the derivative with respect to Qi dot. So I look at when, say, K is equal to I, then I have the whole sum over J of that particular term. And the same thing for K because it's symmetric. So of course these two terms are exactly the same. And so that's just the sum, because it's a half times the sum of two things that are the same. So that's just equal to, let's choose the one with K, of Aik 2K dot. All right, these two terms here are equal. So half times the sum of the two is just one of them. So now in the quantity H, remember what appears in the quantity H is Qi dot times di L by di Qi dot. So let's look at that term. So consider the term sum over I equals 1 to N of Qi dot times di L by di Qi dot. So we just calculated that, right? That's the sum of I equals 1 to N of Qi dot times the di L by di Qi dot, which was equal to di L by di Qi dot, is this thing that we just have here above. That's the sum of K equals 1 to N of Aik Qk dot. And so we're just putting the two sums together. That's the sum over I to n, the sum over k to n of aik qi dot qk dot. And that's exactly the kinetic energy without the half term in it. So that's equal to 2t. So now, again, let's consider h. So this quantity h, the Jacobian integral, which we know from variational calculus must be constant. So that's given by the sum from I equals 1 to n of qi dot di L by di qi dot minus L, right? So we just calculated this first term here to be equal to 2t minus, and then L is t minus v. So 2t minus t minus v is equal to t plus v. So the kinetic energy plus the potential energy is equal to the total energy. So that's a very important result, right? If di L by di T equals 0, then total energy is conserved. So that's just conservation of energy. And of course it makes sense that di L can't change with time, right? If the gravity changes with time, then energy is not conserved. And otherwise it is. So conservation of energy, of course, is very important. And it simplifies solving for the equations of motion considerably when you can use it. So anytime you have what we call a constant of motion, or an integral of the motion, but that just means the same thing, that helps us solve the equations in a more easy way. Right? The worst way to have to solve them is when you do in fact get the Euler-Lagrange equations of motion as second order derivatives, right? Mx double dot equals a bunch of things. That's the same as when you do Newton's second law. But we know, of course, that it's much easier to solve things with conservation of energy if we can. So very formally, since h equals t plus v, right, we can write that t, which generally depends on the q dots, is equal to h, the total energy, minus v, which will typically depend only on the q's. So this means that we can write, in principle, q dot as a function of h and v. Remember, h is a quantity; it's a number. And so that is, in fact, first order differential equation, right? That means that, maybe I should call this a function of h and v. That means that dq by dt equals that function f of h and v. And so that can be integrated where you can do the integral of dt is equal to the integral from, say, qa to qb of dq over that function. and that gives you Q of T. So you don't have to do a second order derivative, but it does assume that you can do the integral of 1 over f integrated over q, and then invert that function to get q as a function of t. Let's do a quick example of using. So this is just a very formal way of saying we're using conservation of energy to solve a problem. So here's how you would do it in practice. This is example 4.7. So it's a simple harmonic oscillator. So the Lagrangian L, so a one-dimensional simple harmonic oscillator. The Lagrangian is a half mx dot squared. Alright, kinetic energy minus the potential energy from a simple harmonic oscillator, which is a half kx squared. Alright. So observe that the Lagrangian doesn't depend on time. There's no t's in there, right? So in principle, we should be able to use what we just found. So let's say that at t equals 0, the position x is given by x0. So we have h, which is equal to t plus v, is equal to a constant. So let's say also that t equals 0, the simple harmonic oscillator was at rest. We impose that as initial conditions on the system, right? So we can calculate h at t equals 0, right? So at t equals 0, we can evaluate h to be a half kx naught squared. This is how you would solve a simple harmonic oscillator problem, right? You could calculate the energy. So you can imagine pulling the mass back on the spring to position x naught, and then you let it go, right? So you can calculate the total stored energy as a half kx naught squared. So now let's specifically use our equation to, let's say, solve for the period. So we want to write that t equals h minus v. So that's a half mx dot squared equals a half k x dot, x naught squared minus v, which is a half k x squared. We can write that as x dot, well, let's keep the squared for now, is equal to k times x naught squared minus x squared. And so that function, f of h and v, right? So x dot, oops, I forgot the m here. So that's going to be the square root of k over m. And times x naught squared minus x squared. All right, that's equal to our function f of h and v. And so now we can write that the integral dt is equal to the integral of dq of f of h and v, right? So the integral of dt is in principle t, right? So let's write t is the integral of x naught to 0 of dx over a function which is square root of k over m x naught squared minus x squared. So we have to decide on the range of integration over x. So if we integrate from x naught to 0, that's actually a quarter of the period, right? Because for a simple harmonic oscillator, if you start at x naught, it will go to 0, then it will go to minus x naught, and it will go back to 0, and then it will go back to x naught. All right. So if I do 4 times that, then that's equal to the period. And that's an easy integral to look up. And so we didn't have to use the Euler-Lagrange equations in this specific case because we recognized that there was an integral of the motion. In this case, the total energy is constant. And so we can simply write out the solution as an integral that you can look up. So in principle, this gives t of x, right? And you can invert to get x of t, which is the solution to a problem. So it's not always trivial to invert t of x to get x of t, but in principle it's possible. And so here's a specific case where it's easy and you get around having to solve a second order differential equation. Okay, so I think we'll stop here because we're at a nice stopping point before we deal with cyclic coordinates. So, any questions about this? So just a reminder that the assignment is due Friday. Next Monday we'll do a review session, and next Wednesday we'll have the midterm. The midterm will be in class, closed book, but you can bring a double-sided page of notes, letter-sized paper. Okay, well, thanks everyone for joining, and I'll see you all on Monday.